Welcome to a new video of heat transfer. We continue our discussion of heat conduction, and in particular today we're studying heat transfer from thin surfaces. Let's analyze the case of convection from a surface. So we know that convection from a flat surface is ruled by Newton's law of cooling. So Q convection is equal H, the convection coefficient, times AS, which is the surface area, times the difference between the temperature of the surface and the temperature of the fluid at an infinite distance. That means at a distance sufficiently far away from the wall. So we ask ourselves, how can we increase Q convection? Let's make the hypothesis that the temperature of the surface and the temperature T infinity are fixed. So we can increase Q either by increasing the convection coefficient H or by increasing the surface area AS. So today we talk about how we can increase the surface area AS so we can increase the convection from the surface. And to do that, we use thin surfaces. So we use fins. So fins are protrusions from the surface. They're very long, thin usually, and they're built with a material with high thermal conductivity. So you can see on the book of Incorbera or the book of Kengel for various shapes and sizes of thin surfaces. Here I've just represented two. Here we have one case where we have a circular cross-sectional area. Here we have a squared or rectangular cross-sectional area. So to study the theory of thin surfaces, we have to make some assumptions. So first of all, we consider steady heat conduction and a system with no heat generation. We have a constant thermal conductivity, and we have a uniform and constant convection coefficient H. And we treat the problem as one-dimensional. And we can do that because, as we said before, fins are usually very thin and slender in geometry. This is a schematic of a fin. So here we have the surface from which we want to extract heat, and we have the situation where the surface is a fixed temperature T0. This is the base of the fin, and this is the fin. So we have a coordinate system where x is 0 here, and we take a small control volume here. So what's the energy balance here? We have some Q conduction that enters the control volume and some Q conduction that exits the control volume. But we also have a loss of heat due to convection. So the Q conduction at position x must be equal to the heat conduction at x plus delta x, where delta x is the length of the control volume, plus the Q convection. We can write the Q convection using Newton's law of cooling, and the surface area is the perimeter times delta x. So the energy balance equations has now this form. And what we can do, we can take the limit as delta x, the thickness of the control volume, is going to 0. So delta Q over delta x becomes the derivative of Q with respect of x. Then we can use Fourier's law because we want to eliminate Q and express Q as a function of the temperature. So we have this expression, which can be simplified because in the case of constant thermal conductivity and also constant cross-sectional area, the equation can be written in this compact form, where we have defined m squared as hp divided by k ac, and theta here is a new variable t minus t infinity. So you can try as an exercise to go from this equation to this simplified equation. The equation that we found, it's an ordinary differential equation with constant coefficients because m is constant, and it's second order, and it can be easily solved in this form. Note that C1 and C2 are unknown constants, and we need to find them to solve for the temperature. How can we find them? We need two boundary conditions. We note we have two constants of integration here, because the equation, the original equation, is second order. So let's see what kind of boundary condition we have. We analyzed two cases, depending on the boundary condition at the fin tip. At the fin base, we always have the same boundary condition. That is, the temperature at the base is always equal to Tb. So theta of 0 at x equals 0 is Tb minus T infinity. So we maintain a constant temperature at the base. Then we have two cases. The first case is the case of infinitely long fin. So in this case we have L, the length of the fin, going to infinity. So the temperature at the tip must tend to the temperature at T infinity. Therefore, the boundary condition at x equal L is TL minus T infinity equals 0, as L going to infinity. It follows that the term E mx, so the term will have to be 0, because otherwise we will have a growing temperature. Growing temperatures x grows large, which is obviously not physical. So we can use these two boundary conditions and we find the solution. So the temperature has an exponentially decaying behavior. What we can do, we can also compute the Q that's extracted at x equals 0 at the base of the fin. So we use Fourier's law conduction at the base, so minus k ac dt dx and x equals 0. So we take this expression and we take the derivative of this expression with respect to x, and then we set x equals 0, we find this expression. And when we note that this Q that we computed must be equal to the integral of h theta x in dA because of conservation of energy. So all the heat that's extracted from the surface at the base must be equal to the heat that's released from the fin. So we can try this at home, as this is a good exercise and good check that we have found the correct expression. So the second case is the case where the fin tip is instead adiabatic, so there's no heat loss at the fin tip. So d theta dx at x equal L must be 0. Because we've seen that when we have an adiabatic wall or adiabatic surface in general, the gradient of the temperature with respect to the coordinate perpendicular to the surface is 0. So in this case, instead, we have a Cosh solution. So Cosh involves, of course, the exponential e to the mx, but also e to the minus mx. In the same way, we can find a Q that's extracted from the base of the fin by differentiating this expression. We can also study the fin efficiency. Often in engineering analysis, we need to assess the performance of a system. So we can ask ourselves, how efficient is a fin? Let's consider the ideal situation, the situation where we have to compare a real fin to an ideal fin. So an ideal fin has an infinite thermal conductivity. So if the thermal conductivity of fin is infinite, then the fin will have the same temperature in any location x. And this temperature will be the same temperature as the temperature of the base. So this is a schematic of the ideal situation. 80 degrees at the base and 80 degrees everywhere, because there's an infinite thermal conductivity. In real situation, of course, we have 80 degrees at the base, but then the temperature decreases. So the ideal case represents the case where there is a maximum extraction of heat from the base. That would be Q fin maximum. That's H times the area of the fin times the temperature, the difference between the temperature of the base and the temperature at T infinity. So this Q fin max is the reference maximum heat that can be extracted. So we can define efficiency with respect to this value of heat. So we define as the efficiency of a fin, and we use the Greek letter eta as the ratio between Q fin divided by Q fin maximum. So Q fin is the actual heat transfer extracted from the surface thanks to the fin, divided by the ideal Q, the ideal heat transfer extracted from the surface when, or in the ideal situation, where the fin is all at the same temperature. And by using this, we can substitute the expressions of the heat transfer from the fin in the two cases we studied. For example, the efficiency for a long fin is simply 1 divided by ml, and the efficiency in the case of adiabatic tip is the tanh of ml divided by ml. To find the fin efficiency, it's always useful to use graphs. And you can find this in the books. So each geometry will have a different graph, and this graph is usually represented in this way. We have the fin efficiency on the y-axis, the maximum is 100. And on the x-axis, we have the letter C, which is a function of the geometry. So you note that the fin efficiency is always smaller than 100%. We can add here 100, the percentage. So let's take an example, for example, a fin of cylindrical geometry, cylindrical cross-section. So C will have this expression. It's a function of the diameter of the fin, of the length of the fin, and of the thermal conductivity. So if the fin efficiency is known, fin geometry is known, then the fin efficiencies can be found through the graph. There's another quantity that's very useful if you want to quantify the performance of a fin. That's called the fin effectiveness. So we have to keep in mind that we use fins because we want to extract more heat from the surface, more heat from the base. So we want to enhance the heat transfer from the surface. So it's important to check that the Q fin that we actually extract from the surface when the fin is present is larger than a heat transferred extracted from the base if the fin were not there. So we call this fin effectiveness, and is denoted by epsilon fin. So the epsilon fin is equal to the ratio between the Q fin, so the heat transfer that is actually extracted from the fin, divided by the heat transfer from the base in the case when the fin is not there. So we can have this expression. So it's important to note that we must have effectiveness larger than 1 if we want the fin to perform, because so we have more heat than extracted from the base. So the fin is actually doing a good job. We're extracting more heat when we put the fin. If we have an effectiveness smaller than 1, actually the fin does not work because it acts as an insulator. So we're actually extracting less heat. So that's not an ideal situation. The fin effectiveness and the fin efficiency are related. So the fin effectiveness is equal to the product of the fin efficiency times a ratio, the area of the fin divided by the area of the base. So again, we can use the expression that we found before for example, for the long fin. We substitute the values in the formulas for the fin efficiency, and we find that the long fin effectiveness is equal to the square root of Kp divided by HAC. So what can we note here? We note that we want to maximize the effectiveness. To do so, we must have, as we said, a very large thermal conductivity, and we want thin and slender fins because we want a large ratio between the perimeter and the cross-sectional area. So a large perimeter and correspondingly a small cross-sectional area. We note also H here is a denominator. So we actually want a low heat transfer coefficient of convection. This means that we want to put the fins where actually needed. So if you're extracting heat from two sides of a wall, and we have water on one side and air on the other, so it's likely that the heat transfer coefficient of convection of air is actually smaller than the one of water. So we need to put the fins to have maximum effectiveness. We want to put the fins where are needed, so on the air side, not on the water side.